Hello everyone. This is a little project I decided to do. It's an idea that Richard and Det had on Learn Electronics Repair. Here it is. This is the thing. What they've done is they've got an Arduino, a rotary encoder, an OLED display, and an MP3 player. And what they have the encoder doing is selecting a track or volume, and it plays samples on the memory thing. SD card, that's it, there we go. And you've got the DAC output. Well, let's just make that bigger. They've got the, they've got the sync. Right, yeah, the reason they've done this is because they want a sync, so when Richard uses it on to test amplifiers, he wants a sync for his oscilloscope while he checks the line out on the left and right DAC channels. They've also put speaker channels on. There's a ground here, but no, don't use that with these speakers, because I'll explain later. But anyway, I like the idea, and I thought I could make my own rather than use an Arduino. I am going to use let's just go out. Let's just use, I'm going to use, let's see, one of these. There we go. It's, get it there, that's better. Yeah, there you go, you can see it now. It's an STM8S103. But, well, why am I using it? When I do my projects, there we go, you can see the MP3 player there, and there's the STM8S103 is down there, hidden behind that wire. Where are we? There we go. Get the light on the right side. Get my hand out of the way. Let's try again. There we go. Anyways, so first of all, I put it all together on my breadboard. Yeah, I've lost track of what I was saying now. Yes, right, the Arduino has lots of memory, and you can use libraries off the internet for the MP3 player. You can use libraries for the encoder. I have these little this is a speaker. I've got a laser cutter, so I've made these little boxes for these things to go in. This is an encoder, so this can just turn like that for an encoder. This is just for my prototyping, of course, and I've got an OLED display here in this little one, and this is the other speaker. This is the right speaker. One thing I've got to do is explain about the MP3 player. We'll come to that in a minute. But anyways, so that's how I do my prototyping. I have these little things. And I've got another little amp here, which I'm going to explain why this is here as well. Yeah, so I do my prototyping. I've also made one for this, but I'm not using that today. Yes, so yeah, what was I saying? Yeah. Oh right, yeah. Using the Arduino. So Richard and Det, they've used an Arduino to do all the controlling, and it's got lots of memory. Well, I say lots of memory, but it's got more memory than this. And you can use Arduino library, so you get the Arduino. Yeah, so they get the library for the what is it now? my memory. DFPlayer MP3, mini MP3. You can get libraries for the rotary encoder. You can get rotaries for the OLED display, and so on. So it's very easy. But with the STM8S103, there's only 8K of flash on it, so we're going to have to write our own code. We can't use Arduino libraries or anything like that. I'm going to have to write my own, basically. And so, I know I'm rambling a bit, but that's what this video is for. And I'll also say, So what I'm going to do is, well, you can see how I do my prototyping just like anybody else on a solderless breadboard, and like I say, I've got my little modules that I've made, so that I need to do the controlling and everything, and then all a network of wires. So the best way to show what I've done is to show it in the circuit diagram. So we've got this. Shall I power it up? Yeah, let's power it up and show you what it does. So just turn everything on. So well, 2 speakers, display is the display. Can you see that there? See if I can just we'll try there. Just trying to get it to display, and then if I move my rotary encoder, let's get it where I'm not got any light on it, and get my bloody mouse out of the way. There we go. Right, so there, so you can see in the rotary encoder that turns. These are just you see these 2 LEDs here. They're just for my diagnostics. I just wanted to see that my encoder was working. If you know how an encoder works, it sort of goes none, then there should be 1, then there should be 2, and then there should be just the other 1, and then there should be none again. And that's how an encoder works. And the sequence, that was just for writing my library for the encoder, that to make sure I got it right. So anyway, so there's the tracks, and what I've decided to do, rather than do it the way Richard and Det did, I'm having buttons. I'm going to put buttons on. I mean, the MP3 player will work on its own with just buttons, but obviously we want to display it so that we can actually choose a track rather than have to just flick through them. So we can actually choose which track we want to play. But I want to design this, because it's an MP3 player, I want to design it so we've got our thing that plays samples, and it also pulses a sync. We may as well have it as an MP3 player as well, so we can use it as an MP3 player. And also, because I want it as an MP3 player, I'll come to the MP3 player in a minute. It has an amplifier on it, but the amplifier is mono. It takes both the DAC signals for the left and right, and it merges them into one, and so you only have one speaker that can attach to it. But I'm going to stick another amplifier on. That's what this little chip down here is, this tiny chip. This is another amplifier. So what I've done is I've hacked into the MP3 player, stopped it from merging the 2 DAC signals through the amplifier on the MP3 player. It just uses the amplifier on the MP3 player for the left channel, and this one amplifies the right channel. So then I get two speakers. I get this speaker and the other speaker. So basically, I've got two amplifiers, one for each speaker, because basically they're mono amps. It isn't a stereo amplifier, so you can't put two speakers on. You can plug headphones into the DAC outputs because that's a very low current. Yes, so I was going to show it play. So I put buttons on for play. So you choose your track like that, and if you press the button, it changes to volume. So you can actually change the volume as well, and see what volume you're at. So you can change your preferred volume. But I've put buttons for play, and I've also done another button for play all. So if you're using it as an MP3 player, you can play all basically. But if you're using it as a signal generator with a pulse, I've put a button to play single tracks, and the button that plays single track will repeat that track over and over again. And then there's obviously a stop button as well. So we'll just have it playing. Oh, actually, no. Stop that. Actually, I'll tell you what I'll do. I forgot we're on eBay. No, sorry, I forgot we're on YouTube. And if I play these tracks that I've got on here, then it might throw wobbly. So I think it's track 20 is the sample. So I've done like a sample. So we'll play the sample. I think. See if this is it. Yeah, it's like a sample. And then we've got the oh, hang on, the I put my hand in front of it. We've got the LED here. So every time it starts, it flashes a pulse for the sync. There we go. I don't think YouTube is gonna. Oh, I'm sorry. I should have said it was going to be loud. I hope that. I hope it wasn't too loud, guys. I apologise if that. Yeah, I should have mentioned that. So anyway, right. Let me just turn all that off then, because we don't need all that. Yeah. So the next step is show you the. No, I'll show you the circuit in a minute. What I'll do is I'll show you how I've hacked the MP3 player so that I can have stereo on my amplifiers. A minute. Right. I've pulled the MP3 player out, and we can have a look. I'm sure we all know what MP3 player looks like. So we've got the SD card on the top, a few passive components here, an LED, and then we've got the main chip. This is the hang on, let's get inside. Yeah, so this big one is the microcontroller that does all the hard work, and this small one is a amplifier, and it's a mono amplifier. So let me just explain about this amplifier. I'll just get this. This is the amplifier. It's where are we? I just want to explain something. Oh no! Tell you what, the other one explains it better. I've got two data sheets, but this is it. You've got the in, and you've got the the out, which is this speaker here, and you've got these. It's coming from two op amps inside the chip. So they're not. None of these. Although it says speaker negative, which is this one here, it's not ground negative. It's a speaker negative, which is pulling from 0 to probably about, well, I'm running at 3 volts, so it'll be pulling to say minus 1.5, and this one will be pushing from 0 to 1.5. So you get the full 3 volt range on the speaker, or just a little less, shall I say. So basically it's a pull and push connection. It's an AB. Is it? No, I forgot what it is now. My memory. I tell you, my memory is terrible. Just give me a minute. Let's have a look. Not that one. Where are we? MP3 player. That's the same one, isn't it? Shit. Okay, forget that one then. There we go. No, this is the other one. Right. Anyway, that tells you. There we go. I couldn't remember what. I'm terrible at memory. It's a Class B audio power amplifier. That means that it doesn't have a common ground on the speakers. It means that one terminal is a negative pulling and the other one is a positive pushing. So basically it pushes, one pushes while the other pulls, basically. That's the simplest term I can say. Right, so this has a better picture though. It's nice and colour. Yes, so we have an input and then we have the speaker output, but it's a mono. What I'm trying to say is it's a mono amplifier basically. So I just want to make that clear. If we go to yeah, so this is our MP3 player. You can see that. So speaker 1 and speaker 2. So you've got the push and you've got the pull. It's not a ground. Forget about the ground when connecting your speakers. I don't know. The reason there's a ground there is because. Hang on, let me see if I can show you this. Oh, I know what. I can show it better on the circuit diagram. Right, yeah, so I've hacked this. Can you see I've put a cable in? So this cable is me right, coming from the right DAC. Well, it's not coming directly from the right DAC. It's coming via a resistor and capacitor. Where's that drawing again? Let's bring that back. Data sheet. It's coming via these two here. This resistor, I can't select that. Can I select it on here? No, I can't. Right, yeah, it shows it better there anyway. So hang on, let's make it bigger. Plus, where's the plus? Yeah. Whoops. Yeah. So you've got your input, which is you've got a common ground on your input. But then you've got your signal, which goes via a capacitor and a resistor, and then goes to the chip. So basically, it didn't show you the underneath. So I'm going to go to, instead of trying to show you on here, where are we? There we go. On there, that's the top. There. So we're going down to pin. It's pin 8. No, it isn't. Because that's 0. Right, so I've got the chip the right way up this time, I think. Am I going right way up? Yeah, there's pin 1, and it's actually pin 4, which is the input. If we look at shit. Well, I'm just done with that. There it is. No, what am I doing? Oh no, here we go. This one. There we go. You see, pin 4. There we go. In. Right. Yeah, and right. Okay. Yeah. So well, you can see from the op-amp you've got an op-amp there, and you've got an inverted op-amp here, and you can see using that these two resistors that they've split the voltage into two, so that's how you end up getting a positive and negative. Anyway, forget that. Don't need to know that. Yeah. Right. So circuit. Yeah, circuit now. Right. Okay. Give me a minute. I'll just. Yeah. Right. So this is the circuit for the of the DFPlayer MP3 player. This one here. This here is the SD card slot. This is the amplifier that's on it, the little chip, and this is the microcontroller, the main brains of it all. So let's zoom into where we need to be, which is around this area. So we need to look at this sort of circuit basically, because what we want to do is make this amplifier just do one channel. So if we look at this, we've got the unknown microcontroller, because I don't have a clue what they used. Well, I didn't bother going searching and working out. But anyway, these pins 13 and 14 are your left and right DAC output. So you did analog converter. So we're getting the analog left and right channel coming out. These two capacitors, these are going. These two go to the left and right DAC pins on the actual module. Let me just bring that up. If I can remember where. Oh yeah, there. Yeah. So and I can't see it. They're not written on it anyway. So hang about. Let me just minimize that. Let's bring back up the. Yeah, that. No, not that one. Oh yes, that one. Yes, there it is. Yes. So if we look at this here, so let's just bring that up. You can see that the pins 4 and pins 5 are your DAC right and left. So that's these pins here. So you got your 4 and 5, which come from the microcontroller, and it also sends them through these two capacitors. So we up to, and these two resistors. So these two capacitors and resistors are. Where are we? Just add that. Right. Yeah. So. Let's have the coloured one. Yeah, so we've got a capacitor and resistor here going to our input. Well, okay, so we've got our capacitor and resistor coming from our signal, our audio signal going through capacitor. So, which is these two. So that's for our left channel. Excuse me. And that's our right channel. And then you can see that they both merge together and they go through this capacitor to our input on pin 4 here. So, which is in line with the, we'll bring it back, which is in line with this, and the other resistor I've got is that feedback resistor, basically, coming from the output. Now this, right, so you can see from this diagram that that is a 20k ohm resistor, and that's what they've used on the MP3 player. That's important because this sets this speaker as an 8-ohm speaker, so that's what you need to put on there. Like I said, this is a, where are we? This is a Class AB audio power amplifier. So the resistance, oh, I've lost it again now. Yeah. So if we've used the 20k ohm, which is what is on the DFPlayer, then this needs to be an 8-ohm resistor, and I've forgotten already. Yeah, Class AB audio amplifier. Right. Okay, remember that. So you need to stick just one 8-ohm speaker on these two pins. If we go to the data sheet, now I've forgotten where it says this, maybe in the instructions. Right, yeah, this bit here. Built-in power watts amplifier speaker. Right, okay, they've stuck the 20k resistor on, so that means it is this, and it isn't 3 watts, it's 1.5, because we've got it set up for this. If you had set it up for the 4 ohms, it would be 3 watts. This is where the Chinese like to put the big numbers. If they'll see a big number and they'll give you a big number. This is what it's capable of. It's capable of 3 watts if you use a 4 ohm speaker. But when I reverse engineered the DFPlayer, it's got the 20k. I might as well explain that. So let's go back to the data sheet. I'm sorry if I'm rambling, but I thought you might want to know. Some people might want to know, some people might not. So I'll just keep going. Yeah. So we need to look through the. No, not this one. We need to look through this one. No, I think yes, it's this one. Well, let's zoom out a bit. Electrical characteristics. Typical. Right. Yeah, so this is the bridge sampler explanation of how it does it. It's a 20 kilo ohm resistor. And it does a bit more. Anyway, you can read it. It's all based around that the setup that's on there. That's a shutdown section. Yeah. Yes. It's more like this, basically. Anyway, I'm not going into that. It's way over my head anyways, so I don't care. Right, so we've had enough of that, I think, don't you? Yeah, so the thing is, it's like I say, it's a mono amplifier. So what I've done is this wire, I have removed it. So basically what I did is I cut through like that. And then I am going to attach my little wire to the end of this resistor, and this goes to my second amplifier. So let's just undo that. So yeah, I have a picture of that somewhere. yes, so this is it basically. This is the little this bottom bit is the little the little amplifier, the simple amplifier. So what we've got here, let's just see, yeah, bring that back up. Right, so what we've got here, let's just make that so I can fit it next to it. There we go. So yeah, we can see our capacitors. Well, actually you can't see them two capacitors. One of them is over here somewhere. Oh, it's here. There's the one capacitor, and this is the other capacitor here. But they go to these two resistors, these 4.7. So here's our left one, and here's our right one, and both these at the moment connect together to right, move along. They both connect to this capacitor here, which is this one here. So what I've done is I've put a cut there which cuts this wire here. That cuts that wire, and then what I've done is I've gone from this solder point here, which is that point on that side of the capacitor, and I have going to link it to this point here, this pin 4 on the amplifier. So basically what I'm doing is well, let's go, I delete that, and then I put a link like that. So basically it bypasses that that capacitor. Okay, and then I put another wire on this one, this end of this wire. Well, I should have left that. Hang on. What am I doing here? Oh, I know. Yeah, then what I do is on end of that there I solder a wire, and I take that, I'm going to take that to the PCB that I'm making. So basically that there, let me just bring it up again, which is, where are we? Oh yeah, yep. So that's this is me wire coming from the resistor, and that other brown wire, get some light on it, so I'll hold it that way up so it's pretty much the same as it was. Let's see if we get some more focus. Yeah, there we go. Let's try, is that better? Try and get some, no, that's too dark. Let's pick some bright. That might be better. There. So you can see that on the end of that capacitor there, I've put a link all the way around to pin 4, and on the end of the resistor I've got this dangling wire which is going to go to my other amplifier, which is at the moment it's this one down here. Basically it goes to the input of that, and that way then we end up with the stereo amplifier, because we've got two mono amplifiers basically. Yeah, so I hope that was okay, and like I said, there's the two outputs which goes to speaker 1 and speaker 2. So we've got, yeah, so we've got this amplifier, and then we've got a copy of that coming from here. Put that back as it was. So okay, right, so our next step is controlling this with what was it? Oh yeah, my STM S8103 little chip, which is well, right, so Where's my pictures again? Yeah, so what we're going to do is we're going to control it with one of these. Let's see if we can get zoomed. Yeah, one of those. So what we need to do is to well, we look at our we've got our I've done my breadboard and I've connected my pins and things. This is a bit of after the fact because I've already configured the pins on there, but what we had to do is well, yeah, so my next step is, right, I knew what I was doing. We know we've got a controller, we know that we've got an I2C display, and I know I've got some buttons. So what I've got to do, what I had to do before we actually ran this is configure our STM 108, no 103 F3 the pins on the microcontroller. It's not like an Arduino. There's well well, there is and there isn't libraries. There is with the STM8S ST Microelectronics, they have done peripheral. They have done libraries for the peripheral devices on the STM. Let me just explain the. Let's go to the STM8. Right. Okay. Right. Here's my STM8. So the thing is with these, the reason I like them, I mean they've only got 8K of memory, flash, but they do have UART, I2C, SPI. What else do they have? Oh, it's all here. Oh, they've got an analog to digital converter. It's got I2C. It's got rail. It's got a clock basically. If you want to, you can add a crystal to these chips if you want, and you can get a more accurate real-time clock. Well, a high-speed clock, shall I say? But there is you can, and it's got the 2 timers in the UART, and anyway, you can see there. But the thing is, you've got to configure the pins. So you've got to decide what you're going to use, or so I say what you need, and see if you've got the right number of pins for it. This STMX pin did this for the cube here. What they call this is a fantastic tool for making sure that you you don't cock it up basically. I tell you what we'll do is I'll start a new instance. Yeah, it's really nice. Oh, it's not that one, is it? Hang on. Let's minimise that, move that a bit. Where are we? There we are. There's my cube. Yeah, start a new instance. There we go. Right, yeah, so you can do a new project. So say you've got a new project and you want to configure the pins, and you need to know what pins you can configure and do. So we'll go a new project, and the first thing you get is a selector of what microchip you're going to use. We can do some shortcuts. It's the STM8S, and I'm doing a 103, and the package, I think it's one of these this package. Yeah, there we go. So right, So you can see there's two packages there. So if you're buying these on eBay, there's one thing to remember is they may not tell you which one they've stuck on. Right, hang on. Let me just get back to this picture. Right, can you see this? See this module? Right, it's got a chip on it. That's the chip there. Right, hang on. There we go. It's an STM08 chip, 8OS103F. Right, and it's the number after the F you've got to watch out for. Yeah, because they both look exactly the same, and if you go on eBay you'll find it looks exactly like this, but you've got to read the fine print and check which chip there is. There's two options. There's the F2 and the F3, and it's a very important number, that 2 or 3. So let's just go back. Where are we? It was this one. Yeah. So you can see that we've got the F2 or the F3, and we look here and the flash. One has only got 4 kilobytes of flash, and the other has got 8 kilobytes of flash. So we need this one. I tell you, I've used every last byte in the chip. I need the 8Ks. It will not work with a 4K. Okay, so we've got that far. So we just click OK. And it gives us a blank chip. Now, the first pin to configure is, well, we have to program this chip. And the one way of doing it, if we go to the system, is use the single wire interface. So we check that. So that pin's taken up straight away. Single wire interface module. It has single wire interface module on it, which can be used to program and diagnose. It's a very clever thing, this single wire thing. It's like serial, but you don't just program it with it or download the hex file. It swim, let's call it swim. You can actually send commands, and it will send information back depending on the commands that you send down it. You can say, what's pin 5 doing, and it will tell you what pin 5's doing. So it's not just a program. The single wire interface module is just not. It's not just for programming. It can also diagnose, and you can get live feedback from it with the right instrument, of course. Let me just where are we? Yeah, it's another thing I forgot to get ready. Yes, I use one of these, ST-Link version 2, and it has, I can get out of it, you can see there, it's got the swim on it. And inside this microcontroller, inside this module is another microcontroller that has, well, it's pretty much the same as this microcontroller, but I think it's a big brother of this. And it has single wire interface, and they both can communicate, but because the microcontroller also has USB, yeah, because this has UART, this processor that we've got here has UART, but it doesn't have USB. But the microcontroller inside this one has USB, so what we can do is we can send commands via USB to talk to the swim, which talks to our little processor here, and we can ask it things and do things. Okay, so that's that out of the way. Yes, so what do we need? Well, I also need I need the I2C, so let's tick that box, and there we go. We've got them 2 pins taken, because these are special pins. pins. Now I'm going to be supplying 3.3 volts to this and run it on 3.3 volts. It can run at 5. Now a little thing about all these pins. If you whatever voltage, normally with a microcontroller, whatever you're running the microcontroller at, the GPIO pins can only deal with that same voltage. You can't have a potential difference from the outside coming in to what it's running on the inside. So all these GPIO pins, basically, if you're running this at 3.3 volts, whatever input you're putting into it needs to be 3.3 volts. If you're running this at 5 volts, then whatever input you need to use coming in needs to be at 5 volts. So it has to be same. If we look at a data sheet from that, you'll probably see there's like 0.3 or something like that potential difference between the internal voltage to an external voltage. Whereas these two pins, I think they're special and they can handle I might have got the wrong chip, but I think these can, if I'm running at 3 volts, these can actually handle 5 as well. It doesn't really matter anyway, because we're running everything at 3.3 anyway. The whole circuit is going to be 3.3 volts anyways, so I just thought I'd mention that. The special pins are these two, and that's why we have our I2C on these two pins. Okay, what else do we need? Well, we need UART as well, because I need UART because I want to talk to the MP3 player and tell it what to do. So we'll go synchronous. No, hang on, asynchronous. There, asynchronous. Right, sorry, asynchronous. So that gives us these two pins. So they're used up. So we're running out of pins. No, we're not, because I'm not going to use any. That many. But basically, that's what we want. And I think I need timer 1, channel 1. But I don't need it as an output. It's all going to be internal, so we'll leave that at the moment. We'll do that by the firmware. But basically, those are the pins that I want. Now, I have an encoder. Right. Okay, let's have a look. Oh, damn, I didn't bring up the picture of my encoder either. Do I have a picture to hand? I mean, we all know what an encoder looks like, do we? No? Yeah? I'm just looking, guys, because, yeah, I forgot. No, that's Bluetooth. What did I use an encoder on? Right, I'm going to pause it while I get my picture, because then otherwise, right, I'll just pause it a minute. Alright, okay, this is my standard encoder setup for the rotary encoders and switch. I've shown it before, and I'll just go through it again. It's an AB encoder, quadratic encoder. It has a push button. If you push it in, it's just a switch, so you've got two terminals for that, and then you've got A, B, C. So C. So you got okay. Just so you know, the pins aren't just named A, B, and C. It's A and B for the AB encoder, the quadratic. C is for common. So it's channel A, channel B, and common. It's not just A, B, and C. Okay, so there's your common. And there's your channel A and your channel B. Now, with microcontrollers. Now, a lot of people, if you're using Arduino, you've got plenty of memory. There's no need to. You can use their libraries, and their libraries will have a debounce circuit. I mean, Arduino's for training. I started on Arduino. I think it's fantastic. They did a great job. But it's a fantastic architecture. It's well. It's the best thing to start on with microcontrollers, but sometimes you need to move on then and do it the I won't say proper way, but I would say the pro way, or the way it's done without, let's say the way it's done without Arduino, right? So yeah, so you've got your A channel and your B channel and your switch. What was I saying? Oh yes, right. Okay, with the small microcontrollers, and when this one we're using is only has 8K of flash. Well, every byte is like gold. It's precious. We need to use as little as possible. And one way we can do this is without writing debounce routines. If we don't have to write a debounce routine, then it's going to save a very lot of memory compared to the size of memory that we have. And so if you're going to make a PCB, or even not, I mean, basically, let's just go back to my little picture, right? So if we take my little my encoder here, which I've made into a module, if we look on the back and look inside, we can see that it's got all the capacitors and resistors at the back. This is my debounce. This means that I don't have to write any code to compensate for any bouncing of the switches when we rotate the knob or click the button. If we do, like I say, there's no need to write debounce code. Writing debounce code is an Arduino thing. It's when you get the kits, you plug in wires. It's as simple as possible. You just get a switch, you connect one wire to one end and one wire to the other end, and all the magic is done by somebody else who's written code for you. So that's what that is. So let's go back to my, where have I put it? There we go. So this is my standard debounce circuit. Now this is my, I suppose I could call it my full circuit, because what I have here, I have 3 resistors from the VCC. Now we don't actually need them if the microcontroller is configured. If the microcontroller has pull-up resistors, internal pull-up resistors, then we can use the internal pull-up resistors to do what this bit does. Which, so what we could do is we could actually no, too much. There we go. Hang on, let's just go from there to there. We could actually just have that. That is what I've actually done with this MP3 player. I've actually used the pull-up resistors inside the microcontroller, but I always have this as my standard. These are acting instead of the pull-up resistors that you can use on some microcontrollers. In practically most of them have pull-up resistors, so it's not always necessary to add these 3. But what happens is when you close one of these switches to ground, we have a resistor going through back to the microcontroller, which limits the current to ground. So basically what happens is when these switches are open and we've used a pull-up resistor, this resistor has actually charged this capacitor, And so when we actually close a switch through this resistor, this capacitor, well, I say slowly, we're talking in nanoseconds, microseconds. It closes this, it discharges this capacitor, and once this capacitor is discharged, then this line going back to the input pin of the microcontroller then goes to ground, or below its switching threshold. And while this is happening, while this is discharging, all the bouncing of this switch has finished. So when this switch closes, it bounces a little bit, but it does all that before this capacitor's just discharged, and so you get a clean signal going back to the microcontroller. Anyways, that's that bit done. I've forgotten what I was actually why I brought that up. Oh yes, right, yes, right. We're back to the not that one. Let's minimize that. Oh yeah, we're back to pin configuration. There we go. Yeah, we're on this. This is what we're on. Let's bigger. Yes. Right. There we go. Yes. So we've got our. Well, actually, where are we? Oh. Yes. So we've got our. I got sidetracked there. Sorry. Right. So we've got our rotary encoder. So we've got our. Well, we've got 5 pins. 2 of these pins are going straight to ground. That's common. But we've got our channel A and our channel B, and we've got 1 from the switch. So we've got our 3 outputs, which is this one. So we need 3 pins on the microcontroller for these 3 pins. That's what I was on with, wasn't it? So right, now then, a little bit about microcontrollers. You can see that these all start with P. So we've got PD, and then we've got PA, and we've got PC, and we've got PB. Well, the P stands for port, and we've got port A, we've got port B, port C, and we've got port D. Now, interrupts. When you're detecting interrupts, it's usually a port, and a port will have 8 pins, depending on the build of the chip. You know, when the manufacturer makes a chip, the internals will be the same. Each port can have up to 8 pins, but when they're making the chips, they might just chop a few pins off or a few ports off, but the main part of the chip is the same, but they've reused. You know, they might put less memory in, or they might put less peripherals in, but they'll create a package basically with so many pins on each port and so many peripherals inside it. So let's go back to my encoder. Well, yeah, sorry guys, I forgot where I put it. Right. Okay, yeah. So we're back to I should have just dragged it across to the side. Right. Okay. So we've got 2 parts to the encoder. We've got the switch part, and we've got the quadratic part. Now, so what we want to do, we want the quadratic part on one port, because we want port 1. When one of these 2 pins interrupt, we want them 2 pins on the same port, and that port to just detect the interrupt. We don't want to put the switch on the same port, otherwise they'll start getting confused. It won't know which switch. You've got to put more code in basically and stuff. So the ideal practice is to keep them, if you're using interrupts, is to keep them on separate ports basically. That's what I'm saying. So what we're going to do, I'll drag that across this time. I am going to, oh right, this pin here, this A1, this is an odd pin. They've added it because it filled up the space, but it doesn't take interrupts. This one does. So we'll have that as an input, and then we'll have this one as an input. And basically what I'm going to do is, these are both on the same port, so we've got port A. I am going to make these, I'm going to make this one, and to use a label, we'll make that quad A, and we'll enter use label, and we'll use we'll call that quad B. So I've defined them for my two my quadratic, my channel A and my channel B on my quadratic encoder on here. So there we've got them two pins. Now I need a switch. Now I've also got some buttons. So what I'm going to do is, I've got a lot of pins, a lot of pins on port C. So I'm going to have all my buttons on port C, because I'm going to have a play, a stop, play all, and I'm going to have the button from the encoder. So what I can do is we'll make this all these inputs. Right, so they're all inputs, and you can see that some stuff on the left hand side of this application have gone red. So you can see that I can't use timer 1. I don't need timer 1, so I don't care. You can see the SPI, the SPI, I can't use that SPI. I don't care, I'm not using it. So it doesn't matter about these red things on this side. This is what's good about this application, is it tells you what is okay and what you can't use. So basically I hope you got the gist of that little application. So I'm going to close this. I just wanted to show you how helpful it is in selecting what pins you're going to use. If you're an Arduino person, all this is done for you by Arduino architecture. You know, when you go to Arduino and you select a microcontroller, this is all done to the Arduino architecture. It allocates so many pins to the analog input. It allocates so many pins to the interrupts. You'd only have 2, because basically what you do is you'd use 2 ports. Excuse me, I'm going to cough like hell. I'm going to pause. Oh, I'm back. Sorry about that. Basically I forgot where I was, because it was a long break there. What it ended up with. Oh, right, I was showing you how very useful this Cube MX is. So I'll get rid of this. That was just to show you. This is what mine currently looks like. Finished off. Oh yeah, and yeah, I've filled all these in. So I've got play, I've got stop, I've got start. Oh, and there's the busy one. Yeah, because we need to know when it when the MP3 player, DFPlayer is actually playing something. So I've got a busy input. There's actually a pin for that, I think, but we could have taken it off the LED anyway. Then I've got my button here, which goes with my quad B and my quad A. Oh yes, I've also got an LED which I've added. So there's an LED that lights up when we sing. So, and I've actually got 3 pins spare. This one is limited pin. I think if we click on it, oh, mind you, it does do all that, but it doesn't have interrupt. I know that because I found that the hard way. And then we've got these 2 spare as well. But I haven't added them because, frankly, I ran out of memory on the well, programming it to do what it actually does now. So I was just hoping that was of some interest to somebody. So then obviously this was done prior to actually doing my board, or during the construction of this mess of wires. Basically, you sort of start off with the basics. First of all, you get your screen working, then you get your encoder working, and then you get your communicating working. So I suppose the next step is to show you what I've done here. So the easiest way to show that is through through a schematic. Let's turn all this into an actual schematic. Where's that? Yeah. So this is my schematic. Now I do like KiCAD. I use KiCAD because it's on my machine. It's not on the internet. There's a lot of how can I put it? There's a lot of software on the cloud. You can go on there, you can share it with people, and you can do it. And you usually find the free stuff is with the people that make the PCBs. I use KiCAD because it's I use PCBWay, and I have, if we go to the PCB editor, once I've done my PCB, I just click this button and bingo, everything's done. All I have to do is decide the little options and everything. I'll do that later. Oh God, I'm going to cough again, sorry. I'll just pause it. Right, I'm back. I've cut down on my coding, which is that used to stop all my coughing. Right, yes. So yeah. So let's have a look. So I've added all the. Basically, the way I do this is I just count up all my components I have. Let's move that down. There we go. There, I can click my Twitter. Basically, what I do is get the glare off. What if that's too? Is that too dark? Maybe that's better. Try there. No. Try there. Oh, I'll leave it at that. Stop playing. Right. Yeah. So, oh well, my MP3 player's missing from there. I unplugged it. But basically, I just count all my components first. add all my components and then just string the wiring together. Now a lot of this is analog, so that's why all the wires are joining everything. You could be lazy and not do this. You just give it a speaker name. What I could do is I could just give it the name there, cut that wire and put the name here and here, and it would automatically link the two together. But I've heard, well, there's, I don't know, it swings and roundabouts. Like I say, I put my D bounce in, so like I got my switch, I got my resistor and my capacitor. They all fit together anyway, so and I could have just left that. Why have I put that name there? Ah, damn. But I should have put these elsewhere. Hang about. Yeah, they are supposed to go there. Oh, I like things to line up as well. Yes, that's how that was supposed to go, because I don't want two names on the same. My memory. Where's my memory? Can I narrow that? No. Right. Okay. So I just noticed that it didn't really matter. Like the wires count. But hang on, let me just update that. That hasn't messed everything up, has it? Let's have a look. Where's my switches? Yeah, there's my switches. Oh, crap. No? Oh, well, let's just have a look at them. Oh, no, that's alright. It didn't update that. Right, no, yeah. I did a bit of editing. Because there's like a global library, and then there's a local version for this, because basically I don't want all the silk screen over the top of the components, so I've actually edited it for this thing. Right, okay, back to the schematic. Yes, so basically it's just laying it out. Now we've got our STMA S103F here. I should really call it an F3, just so that we get that right. Because, like I said before, the 3 and the 2 here make a big difference, and this will only work with the F3 because it needs all 16 kilobytes. And we've got our microcontroller. The other good thing about these microcontrollers is I don't need a lot of components with it. This is it. It's this. That all you got to do is add that and that. That's the only two components for that microcontroller to run. It's just that capacitor, and this is just to pull the reset up. so we can reset. Basically, I have a reset pad. I'm not putting the button on. I just need a pad if I need to externally reset, and this pad is actually for programming. So I have these. I have the VCC, the reset, the ground, and the swim button. They're pads, so I can connect my programmer to program it. So that's my basic stand-up setup for the STM8S controller, and then the rest is however we've configured things. So I have put the play all, the stop and repeat single button on, and these have the debounce. I've put my encoder, so these have the 3 connections going to the correct thing. Correct pins, and they have their debounce, the 3 capacitors and the 3 resistors. Let's go back. All right, the MP3 player, it can run on its own with just buttons, and so there is an X and a volume button. They're combined, and they're on the what do they call it? They're on these two pins. So you can connect these 2 pins direct to buttons. So when you're creating a PCB, the real estate, it doesn't matter how many components or whatever you put on it, it's going to cost you the same anyway, unless you actually add in the components. But the actual PCB, the board itself, it doesn't matter what is on there, you know, how many holes or how many tracks that are on there, it'll cost the same. There'll be no change to the price of the PCB depending on what tracks and holes you've put in it. So you might as well have these 2 buttons. I'm not going to use these buttons for the signal generator, but they're very useful if you're using it as an MP3 player, so I've added them 2 buttons as well. Right, so this is our MP3 player. Now the output for the DAC, the digital to analog converter, so we've got a left and right, and it also uses the ground as well. So what I've done is I've used a standard 3.5mm jack, and we can just put a jack in there. We can make our own lead up. If we want to connect that to our oscilloscope, we can make a lead with a 3.3 jack on it, and the other end, whatever we want to plug into our oscilloscope. We could just put little hooks, clip-on hooks or whatever, just to clip to the probes or whatever. But you know, I thought, well, just a standard 3. It's an audio jack, and doing it this way as well. Also, if you have some little you know, the little earbud headphone things, the cheap stuff, you know, the sort of ones for £1, you know, little packet that lasts maybe a week, a month. You can plug them straight into it as well. So it gives you that option. You can just plug some little headphone things in there. I don't have any about. Show you what I mean. Have I got any about? No. But I'm sure you know what I mean. Some little headbuds. So that's why I put a 3mm jack on there. Now the speakers, like I said, I've added an amplifier. So we've got the amplifier here, and this the MP3 player also has an amplifier on board. So it has the 2 speaker wires coming on. So what I've done is I've wired them to another. I mean, I've used the stereo one because basically I bought a packet of 20 or 30 cheap. They're all the same, and buying mono ones is the same, basically the same price as buying stereo ones. So although it's a stereo one, it's mono, and this is not to ground. These two are not to ground. Where have I got one? Yeah, I must have one somewhere. I should have sorted one out first. Anyway, you know what a jack looks like. Oh, I got it. Hang on, I'm just going to pause. Alright, I'm back. Yeah, so we know what a 3.5 mil audio jack looks like. So stereo one, you've got your slave, and then you've got your ring, and then you've got your tip. So what I've done is I've connected the ring and sleeve together. So if it was a mono one, this would be just one big long sleeve. And so basically these two are connected to one side of the speaker, and then your tip is connected to the other side of the speaker. So you would you could either use a stereo one or a mono one. If you use a mono one, you've just got two connections, one for each end of the speaker. If you've got a stereo jack, then these two would be connected together. So you know, the other end of the wire would be, the left and right would be connected together to make one connection, and then the other one would be connected to the other. You get my meaning. So that's what I've done there. You can just use a jack to plug in some speakers. And as I say, I've added another amplifier, because the way these amplifiers work, it's a push-pull thing for your speakers, and then there's the other speaker goes into the original DF MP3 player, goes to one other speaker. So I've added those jacks there. Now, as for the signal, what I've done, well, the microcontroller is going to flash an LED, but every time it flashes that LED, you can tap into the LED to get a sync connection. So I've actually made this connection myself. If we take a look at that, where are we? Footprints. Yes, so I've actually made my own footprint. This is the other thing about using KiCAD. I've got my own library, and you can make footprints, and we can look at that. Basically, what that is I've done this. I've made a ground tab and a probe tab, and I've put two holes in the tabs, so you can stick a little loop of wire, so you can either hook your probe onto that, and you can put your clip onto that, basically. So you know, your standard where are we? Let me just bring that picture up. There we go. Yeah, so well, I'll get a probe. Yeah, you know what I mean. You've got your standard probe, you've got a clip on that one there, and then you've got your crocodile. Clip your other probe on, so they go quite easily onto yeah, they go quite easily onto that. So that's what I've done for that. I've made my own little connection. For that, right? Yeah. So that's that. You know, so like I put like I was going to just make a pad on its own with a hole in, so you can clip, and then a crocodile on there. That's why I've drawn it like that. But I decided to go for the 1 mil wire hook things. Then we've got the peripheral resistors that we need, and that's it. Right, now because I'm not actually... oh, well, I need to go back to the pictures again. I'm going to cough again, sorry. I think I'm going to have to start taking more code here again. Right. Yes, so... yeah, so if we look... so basically I'm not using let's get there. I'm not using one of these modules, I'm just using the chip itself. The chip is going to go direct onto my PCB I'm making, so there's not going to be any way to plug in power. So to do that we need to put a socket for power. So what I've done is I've put a USB mini. I put a USB mini because it's an input. This is an input. There's different types of plugs for USB. Some plugs are outputs and some plugs are inputs, and this is an input. A mini is an input. You input stuff into a mini USB. So that's what I've done there, and all that's doing is feeding the 5 volts and the ground into the system. So we've got our ground just going onto our ground plane, and then we've got our 5 volts going in, which if we go through a diode. I've put a diode on it. This is a protection diode. It's so we don't reverse the polarity of... we don't send any voltage going the other way. We don't want to be sending anything back to the USB. USB only wants to be coming in, as I said, and that goes into a voltage regulator. So I'm adding a voltage regulator, and we could use 5 volts here. I've knocked it down to 3.3 because basically every time you send some voltage through something, you're going to lose. You may lose 0.6 volts, or I don't know. I should actually. These are probably Scott. I can't say that word. Scotchy. What? I don't. It's the ones with least voltage drop. And they go in, so you're going to lose a voltage drop here, and then you're going to... so this, if it was 5 volts and I wanted 5 volts, I won't get 5 volts out of 5 volt voltage regulator. You can't stick 5 in and get 5 out, basically. So that's why I've gone for the 3.3 volts. It all runs the same, but it just means that I have any... well, you can see I've got a lot of diodes here, basically. This is because there's 3 ways. No, not that way. I've got 2 diodes here. That's because there's 2 ways of putting power in. I also want to be able to put power in via a battery also. Yes. Right, I want to put voltage in via a battery, but I don't want to add any battery circuitry. I'm going to use a rechargeable LiPo battery, but I'm going to keep that circuitry separate from this thing. I'm going to have it as like a daughter board or something separate. I just didn't want to complicate things. I wanted to make this pretty simple. So that's why we have our mini input power. And then we have our 2 diodes, so that this does not send power to the battery, and the battery does not send power back through a USB cable if it's plugged in. So that's what the diodes are for, and they go through the voltage regulator, and they power everything. And I have an LED to say that we've got our CC power, and I've got an LED to say that we've got power plugged into it. Actually, I might change that. Usually I make them yellow, or do I make them yellow? I don't know, I might change the colours. Anyways, a rabbit in there. So we have our power circuit, and that's about it really. So once I've got it all looking pretty, I do like things to look pretty and sort of easy to see it and route. We could have just used the labels to join everything, but with this one I think it looks better like this. So right, the next bit. Well, I think I'm just wondering whether to make a part 2 or not. No, I'll continue a bit more. Let's go. Right, so once you've got the circuit done, then we need to just put it all onto a PCB. So let's have a look at the PCB. This is my PCB. Now, when I start drawing a PCB, what I will do is, if we go to edge cuts there, right, and what I will do, first of all, is pick a size. So normally what I would do is I would go like, let's just go millimeters. Yeah, I would sort of probably draw a box there about 100 by 100. Now that there is when you're going to PCBWay and prototyping, you get some cheap prototypes for boards that are within 100 by 100. Well, actually, in practice, they want to be sort of 99.9 by 99.9. If they're within that, you get into the $5 range, and that's what I did. So basically, that's what I did here. This is actually just short of 100 wide, but I've only made it 50 deep, so that's quite a nice board there. Lay everything out where you want. Now, I'm going to leave it at that because if anybody wants me to go further into detail of actually using KiCAD, I can make a part 2. But basically, what I do is, all I'll say at the moment is, once you've done it, make sure that you run design rules, run a design rule check, and if you get 0, 0, then all is hunky-dory, and you can, it's cool. The other thing I will say is about designing your own boards is choose an editor where you've got all the footprints and everything, and the models for all the footprints, so that you can then go to your 3D view. That's on the other monitor. Go to your 3D view, and you can then have a look at it, and you can then check it out. I do highly recommend this because the first time I did this board, you see, I've made it so that it's going to go in. It can go inside a box. So these are all flush to the edge. Make sure that any cuts that need doing. So you can see that these speaker ones actually need a cutout in the board there. So make sure they're all okay. When I design the board, like I said, I'm going to add power, but because the box, let's just look at that on top. Nope, where are we? There's there. That puts it in plan, right? Okay. So you can imagine that I've made it so that the box edge of the box is going to go along this face of this PCB, and these are going to stick out the box. Same on that side, and same on this side, because there's going to be an SD card going in there. This doesn't really matter, but basically the box has got to fit exactly inside a box so that you can access these pieces. And I said that I was going to add a battery, and the battery will go underneath it. And so this cutout so little things like this cut out here, so that the wires from the battery can come from the underneath and plug into the battery connector. And also, now that we've done it 3D, you can check that nothing's going to foul this connector. So this is the connector that I am going to plug that loose wire into. That comes from the DAC on the MP3 player, and that will go into this little socket here. And you can see that the screen looks alright and it's not fouling anything. And you can see I've placed my microcontroller underneath. You can check all the silk screens that they're not running through everything, but the DC the checker button will sort that out. It'll tell you. And basically you can actually see what you're going to actually make, and it's going to look just as you envisaged it. So I hope I could do with changing that colour to blue. Yeah, so yes, I do recommend being able to view it in 3D, and you can actually see what it's going to look like, and you can see all your labels, check it all out. These are the 2 extra buttons. You can see DFPlayer for datasheet for them 2 extra buttons. Now, as I was saying, I'm not going to use them for this, so those 2 buttons, you don't have to fit them, but the option is there. I always add the option if necessary. Oh, and talking about options, there's these 3 little connections here. So what we've got: ground. Most people guess what this is. Ground, D+, D-, and P. So we've got our positive, VCC. We've got our ground, and we've got USB D+ and USB D-. So I'll go back to the actual circuit diagram to explain them. Yes, they are here. There we go. So that's these 3 here. Now, like I say, when you're designing a PCB, if there's an option, you know, you can say that, right, I'm not going to use that pin, right? So basically what I can do is I can go up, where's my, right. So remember my PCB, my microcontroller, right? Let's just bring that back up again, right? There's my microcontroller. Can you see these 3 pins here? There's nothing connected to them. But then you can think, well, maybe later in the day I might find something I might want to attach to them. But if you don't put any pads connecting to these, then you're not going to be able to do that. You're going to have to. Oh, these pins are really small, so I've tried soldering to them. They're really small. They're not the easiest thing to solder. But if I put 2 pads on, so there's the 2 pins there. If I put 2 pads on, and they're made with the PCB, then they're there. I'm not going to use them, but just in case one day I might decide to use them. So what I'll do is I'll add them there. So you can see that I've got them 2 pins, 2 pads there where I can add wires to, and maybe add something extra another day. I'm not going to add anything now, but you never know. I might use them. I haven't done this one. I forgot. I should have put some on there as well, so then I could use that for a later date. But that I should have, yeah, that's something I forgot. Anyways, so yes. Now then, let's. Where is it? Right. So the thing also, I'm rabbiting. I'm just trying to remember what I'm talking about. Right. Yes. yes, if we bring back the MP3 player module, right, so that's the module. If we scroll down, there we go. Right, yeah, it supports SD card, so we can have SD card. Well, that's actually on it. That's that thing there. But it also supports a 32 gig USB flash drive. Well, a flash drive isn't going to plug into the SD card slot, is it? So I have actually put where are we? Yeah, so you see we've got the USB here. So this is the MP3 player. There we go. So we've got the USB plus. So we can actually plug a USB drive into these and connect to these two wires. So what I've done is I've added a couple of passives there, and I have put them onto these 4 pads. So what we can do is we can maybe put another USB socket to the project and wire them up to these 4 pads. So these 4 pads are for plugging in an external USB drive. I'm not going to do that because the what have we? Let's have a look again. I think that the 32 gigs on the micro SD card is enough, basically. So I'm not going to do that. And also I need some more code to tell it to do this. Well, actually I just need to send a command and it will read from the USB flash. If we look at the commands, where are we? That's that, and then we go down. Oh, hang on. Anyway, there's a command somewhere that says instead of coming from the SD card, go and read the USB flash drive. Anyways, and this is all about commands. Right, now then, so my next question is, yeah, what I am going to do is, I am going to leave it at that now, so let's just view our 3D model. Yeah, nice model, there we go. Right, so at the moment I've sent the boards off. Well, I've sent the files off to get the boards made. They're still to come. I know I've been rambling. I do ramble. I know this is a long video, probably. So my next question is, does anybody want to know more about creating well, we'll stick with this project, so using KiCAD to create this model. And does anybody want to know more about let's have a look. Yeah, so this is my code for this project. Ignore the name because basically I was making this as a standard project and it got turned into this project, but I'm going to use this as a template, that's why it's named like that, but the code is for this project. Now, as any regulars that watch my videos will know that I like to use Visual Studio to do all my editing. And if anybody wants to know what I'm going to say, well, do you want me to sort of do a video of me writing the code for this project? Like I say, I don't use the editor here. This is just for sort of compiling. I just compile the code on here, compile it on here, and then although this has a programmer, I can click programmer, and then I can just program the chip, but cancel that. But I don't use that. ST Microelectronics also have in the package. Have I started that up? Yes. Also have in the package a programmer, and basically this just programs. All you have to do is load the file that you've created. Created in here, but I don't use the programmer in here. What I do is I create the file and then I load it into the actual program. The reason being, I can see how visually I can just look and see roughly how much space I've got left in the memory. It's also got a bit of EEPROM, so we can store stuff in there, but I haven't put out in there. And then we've got our option bytes and we can set them. But basically this is the main thing. The reason why I program using this and program it is because basically I'm looking to see how many notes I've got left. This is the size of the program. This is my flash, and basically as I start, it starts filling up, and then once I come towards the end of doing the program, it sort of overflows and I can't stick any more in there, so then I find ways to tweak the program to reduce the amount of memory I use. And this is just a quick visualization, and that's why I use it. So my question is, I'll get back to it eventually, is does anybody want me to do another video of me doing more with KiCAD to create this PCB, which would involve actually making a component like you won't find a component like this on the internet. You know, a footprint that looks like this. I've created this footprint. Like I created this footprint here also. And that's what I like about this. I can create my own footprints. I have a box full of old junk, where old parts from old things, and you don't find the footprints for them on the internet, so you can make your own. And it is a good way to visualize that your finished job is going to look right as well. So does anybody want me to make another a part 2? And say maybe a part 3 where I actually go through creating the code, because there's more to it than Arduino. Arduino does a lot of work for people. It does a lot of stuff. In Arduino, all you've got to do is basically you create the functions. So you would just do something like this in Arduino, where you would send a command to a library. So this would be part of a library, and you just send that command, stop track, and that's it. But when programming on a microcontroller using ST's Visual Develop like this, you've actually got to create your own files. So like this. This is for the I2C. You don't have to go completely down to the bare metal of programming the chip, because ST have actually done a peripherals library for this. So if we look down there, they've done a standard peripherals library, and you can use all these actual libraries for all the peripherals on the chip, like the I2C, the UART, the timer. So I'm using the timer 4. They've already done this for you, and so you can use these. You don't actually have to get the actual data sheet of the STM8S and go bare metal. The bare metal bits have actually been done for you. You just use these libraries and and your own code, basically. So does anybody want a video on the code side of things, or on the PCB side of things? I think this has been a really long, laborious video, but I thought I would do it. And if you made it to the end, well, congratulations and thank you very much for watching all the way to the end. I'm going to leave it at that because I'm starting to ramble again, like I did all the way through. Okay, right. Okay, I'm gonna stop it. Okay, thanks for watching, guys.